Now that you know quite a bit about how to say what you expect a random variable to be, we're going to do the next step that we always do when we make some kind of estimate, which is to give a margin of error. Any estimate in statistics, as you've seen in Stat 2.1, is only useful if it has a margin of error attached to it. Otherwise, you could just guess anything you wanted. So we will start today talking about how far off your random variable is likely to be from what you expect it to be. And we'll start with a little example. So I have a list of 4 numbers, 1, 2, 2, and 3. You can imagine them written on tickets in a box, and I'm going to draw ones from that list. So I have chance of a quarter of drawing a 1, chance a half of drawing a 2, and chance a quarter of drawing a 3. And that's my probability distribution table there. The expected value of my single draw is just the average of the box. That is something we've discussed before. And now what I want to do is find out how far off the numbers are from this expected value. Which numbers? Well, actually, I'm only going to draw 1. But it could be 1, in which case it would be off from 2 by -1. It could be 2, in which case it would be off by 0. And it could be 3, in which case it would be off by +1, and that is something I can represent in a little table. I'm looking at my variable and subtracting its expected value. This error is called a chance error. It's due to chance. It's due to which of these 3 possible values Tyche decided to pick. And here is a distribution table for that chance error. Value 1, picked by Tyche, expected value is always 2, so the difference is 1 minus 2 is -1. 2 minus 2 is 0, 3 minus 2 is 1. So if we want to get some sense of how big this chance error is, a natural thing is to take the expectation of the error itself, just to take the expectation from this distribution. And what happens when you take the expectation from here? That's -1 times a quarter, plus 0 times a half, plus 1 times a quarter. Or equivalently, you could just average -1, 0, 0, and 1. And what do you get? Yep, you get 0. Now, for this particular distribution, it's apparent that the errors are symmetric around 0 and your expected value should be 0. But you know, this fact that if you look at the chance error and you take its expected value, you will get 0 no matter what list you started with. No matter what the distribution of x, the expected chance error is 0. Does that seem like a familiar result? It ought to. The expectation is analogous to the average. This chance error, then, is analogous to deviations from the average. And a long time ago in Stat 2.1, we said, if you take the deviations from the average and you average those out, you are going to get 0, no matter what list you started with. This is exactly the analog of that result. So where does that leave us? We're trying to get a sense of how big the chance error is. We've just discovered that if you take its expected value, we're going to get 0 no matter what. But that's not helpful, even if it's correct. We want to know roughly how big the chance error is. We don't care if it's minus or plus. We just want to know how big. And so we have to get rid of the sign. It's the sign that is causing the cancellation that's leading to the 0. And how are we going to get rid of the sign? Oh yes, you now remember this from Stat 2.1. We are going to square that chance error. And we're going to be a little bit careful here. When you square the 0, you get 0 again. So this 0 squared is the 0 here, and that probability of half is translating over to here. When you square -1, you get 1. When you square 1, you get 1. So both of these original cells of -1 and 1 are bringing you, via the square, to 1. And that is why the total probability that your square is 1 is a quarter plus a quarter, and that's a half. And now I have a random variable whose values are non-negative, and I'm going to take the expectation of this thing. This is 1, 0 and 1, 1, equal proportions, and its expected value is very clearly 1/2. And there I have it. 1/2 is the expected squared chance error. And that's the good news and the bad news. The good news is it hasn't all cancelled out to 0. The bad news is, as with averages, I've ruined my units. If these were amounts in dollars, then the errors are amounts in dollars and the squared errors are in amounts of dollars squared. We don't like that because we don't understand dollars squared. Nobody does. And so how do we fix that error? Yep, we take the square root. And the square root that we're going to take has a name. It's called the standard error of x, abbreviated to SE of x. And it is the root of the expected squared chance error. And in this particular instance, it is the root of 0.5, which is about 0.71, 0.707 something. And it's worth observing something that you will have noted already, is that this number is the SD of the list 1, 2, 2, and 3. How would we go about computing this SD? We'd first compute the average, that's 2. Then we'd take the deviations from average, that's exactly what we've done here. Then we'd square the deviations, that's what we did here. And then we'd take the average of that. And then finally we'd take the square root. That's exactly what we've gone through. That's the same process. And what we have calculated is what is called the SD of the box. So if you have a single draw from a box of numbered tickets, then the expected value of that draw is the average of the box. The standard error of that single draw is the SD of the box. And this is purely calculation. For the rest of the segment, we're going to try and see what this thing means. Now first let's look at a formal definition. So you've got a random variable, an arbitrary random variable x, and you are defining its standard error. And we said we're trying to get a sense of how far off x is from its expected value. So first you calculate that difference, which is the chance error. You square it so that you don't have a trouble with minus errors cancelling out plus errors. You take the expected value. That's a measure of how big your chance error is, except because of the square, you've messed up your units, so you take a square root. And what does this measure? It measures roughly how big the chance error is, roughly how far off your random variable is from its expected value. And you will recall this is exactly analogous to the standard deviation of a list of numbers. What was that? That was the root mean square of the deviations from average. Yeah, it's coming back from the mists of Stat 2.1. That's right. So, you have a list of numbers, you have its average, analogously the expectation. You look at the deviations from average, which is now the chance error, how far off your random variable is from the expectation. You squared the deviations, so you square your chance error. You took the mean of the square of the deviations before, you take the expected value of the square of the chance errors now, and you take the square root after that in both cases. And what did the SD measure? The SD measured the rough size of these deviations, roughly how far off the numbers are from the average. And so now you have replaced average by expected value. And so what you're saying is that the SE is essentially an SD. In fact, in many, many textbooks, this quantity here is simply called the SD of the random variable x. They don't even bother to make the distinction. In our course and in your text, we'll make the distinction that the standard deviation applies to a list of numbers, whereas the standard error applies to a random variable. Regardless, the standard error is an SD, and therefore it has all the properties of SDs. And the crucial property of the SD is reflected now in this way. How far off are the numbers from the expected value? no matter what the shape of the distribution of x, so no matter what list of numbers you're drawing from, with high probability, your random variable will be in the range expected value plus or minus a few standard errors. Do you recall? No matter what the shape of the histogram, the overwhelming majority of numbers in your list will be in the range average plus or minus a few SDs. We've made exactly the same statement here, but in the case of random variables. And in the case of lists of numbers, what was it that made this statement precise? This is a statement that we kind of understand, but it's a bit loosey-goosey at the moment. What was it that nailed it down? Who was it, I should say? It was our friend Chebyshev. And here is Chebyshev for random variables. The probability that your random variable is k or more standard errors away from the expectation is at most 1 over k squared. You remember this bound from before. Another way of thinking about this is if you look at the probability that your random variable is inside the interval expected value plus or minus k standard errors, that probability is at least 1 minus the Chebyshev bound, 1 minus 1 over k squared. And if the k's are bothersome, let's take k equals 2. Let's look at the chance that your random variable is in the range expectation plus or minus 2 standard errors. Well, Chebyshev says that's greater than or equal to 1 minus 1 over 2 squared. So 1 minus a quarter, that's 3/4. And this is the same result that you had before, which is that if you look at a list of numbers, any list of numbers at all, then the proportion that lies in the interval average plus or minus 2 SDs, that proportion has to be at least 3/4 no matter what the shape of the distribution. Same result, just for random variables. And while we're about it, how about going 3 standard errors on either side of the expected value? So you stand at the expected value and you walk 3 standard errors on either side, you will pick up at least 8/9 of the probability. 1 minus 1 over 3 squared. Chebyshev, just as you knew it for lists of numbers, now being applied to random variables. The proof is essentially identical. So this is true no matter what the distribution of x, and this is what makes the standard deviation or the standard error a useful measure of spread, because you can actually quantify probabilities of ranges regardless of the shape of the distribution if you're using the expected value and standard errors as your measures of center and spread. But you know that if you know a bit more about the distribution, you can be a lot sharper than these bounds. In particular, if the distribution is normal, you can do very, very well about approximating probabilities of intervals. And so now we're going to build up towards that. And what we're going to do is we're going to stick with random sums, because those are going to be fundamental examples when we look at sample averages and so on. And so here is a result on the standard error of a random sum. And before we get to that, let's remind ourselves what we know about sums of random variables. So what's the basic setup? You've got a number of draws, n draws, at random with replacement, and I'm putting this in red now because it's going to be quite important, from a box of numbered tickets. And I'm going to call the average of that box mu, that's mu, the Greek m for mean, and the SD of the box sigma, which is the Greek s. What you saw in the last section was that the expected value of the sum of these n draws is the number of draws times the average of the box, which in my notation, for those of you who like the math language, is n times mu, number of draws times average of the box. So that's what you expect it to be. But expected, give or take what? There's got to be a margin of error there somewhere, and that's the new thing. The standard error of the sum of the draws. The sum of the draws is a random variable. It's got a standard error. And luckily for us, that standard error has a very simple formula in terms of these ingredients here. I'm repeating if the draws are with replacement, that is to say if you have independent draws. Then we've got this formula for the standard error. If the draws aren't independent, the formulas are more complicated later in the course. If your draws are with replacement, hence independent, and each of them has standard deviation sigma, then the standard error of the sum of the draws is square root of the number of draws times the SD of the box. Formula very analogous to this one, just you're not multiplying the SD by the number of draws, you're multiplying it by the square root of the number of draws. This square root that appears in measures of error is something familiar to you. It's coming from the definition of the standard error having a square root in it right at the end. That thing doesn't go away. And you remember a root that popped up when we were doing root mean square errors of regression. Do you remember the root 1 minus r squared times the SD of y? Pretty much every measure of error that you have in probability and statistics, at least at this stage, has that kind of square root lurking in it. So in the end, what's the summary? You've got draws at random with replacement from a box. You know the average of the box, you know the SD of the box. You expect the sum to be number of draws times the average of the box, give or take, square root of the number of draws times the SD of the box. Now, I haven't proved this result by any means, and I'm not going to prove it here. This one I'm going to ask you to take on faith. There's a sketch of a proof, in fact, probably even a complete proof in your textbook, for those of you who are algebraically minded. What we're going to do here is an example. And this is an example that we started out with in the previous segment. You've got a die being rolled 200 times, and we're looking at the total number of spots. And we discussed that this was an artificial example, but it contains the heart of the calculation. And after this example, you can do more interesting ones. But it's good to start with something simple. Right, so you've rolled a die 200 times, and you want to know what you expect the total number of spots to be. And now you also want a margin of error. So how do we do this? Well, we know that our total number of spots is like the sum of 200 draws from the box 1, 2, 3, 4, 5, 6. And now we've got a machine that figures out how to calculate the expected value of the sum and the standard error for the sum. The tickets in the box represent one trial, what you can get on a single trial. In one roll you can get 1, 2, 3, 4, 5, 6. So let's examine that single roll first by calculating the average of the box, 3.5. In the long run you expect about 3.5 spots per roll, give or take. The SD of the box. Now how do you calculate the SD of this box? It's just the SD of this list of numbers. So it's the root mean square of the deviations. The first deviation is 1 minus 3.5, and I square it. The second deviation is 2 minus 3.5, and I square that, and so on till the sixth deviation. I take the mean, that is the average of all of those, and then I take the square root. So this is my old formula for the SD, and I get 1.71. A word of caution. Those of you who did not take 2.1, note the divisor. It is 6, and it has to be 6, not 5. Do not drop that by 1, because you will make a mistake here. The division by 5 is weighting. We talked about this in 2.1. It does not apply until you're doing a particular kind of statistical inference. Until then, the definition of mean as dividing by the number of elements in the list is exactly the definition that you need. So what have we got? We've got, if I look at a single draw, I expect it to be 3.5, give or take 1.71. But now I'm looking at the sum of 200 draws, and by formula, I expect the sum to be number of draws times average of the box. That's 700. That's something we've done before. And the new thing that we have now is that the standard error of the sum is the square root of the number of draws times the SD of the box. And that's about 24. And so in the end, the statement you've got is if you roll a die 200 times, the total number of spots is expected to be 700, give or take 24.18. So give or take about 24. And I want to take a look at those numbers for a bit. You'll recall that a couple of segments ago we'd said we expect the total to be 700. What's the smallest it can be? The smallest it can be is 200 if each of these 200 rolls shows one spot. Unlikely but possible. The biggest it can be is 1200 if each of these shows 6 spots, equally as unlikely but possible. And this 700 is exactly in between 200 and 1200. So the possible values are in the range 200 to 1200. What about the likely values? What about the probable values? Well, let's take a look. We're saying 700 give or take about 24. Let's say 700 give or take about 25. It's an easier number to handle. So what does this mean? Well, this means you expect the majority of the probability to be in the range 700 plus or minus a small multiple of 25, roughly. So the range 700 plus or minus 25 is likely, the range 700 plus or minus 2 times 25, plus or minus 3 times 25, plus or minus 4 times 25 if you really want to go out there, but beyond that, what have you got left? Outside the range, expected value plus or minus 4 standard errors, Chebyshev says there can be at most 1 over 4 squared. There can be at most 1 over 16th outside that range. Well, that's pretty small. So in the range 700 plus or minus about 100, you expect almost all of the probability. You expect the probabilities to be concentrated in the 600 to 800 range, even though the possible values are in the 200 to 1200 range. So possible values, 200 to 1200. Probable values, by this calculation, about 600 to 800. You don't expect stuff outside that range. And that's an interesting observation which is repeated in a famous case of tossing a coin 100 times and looking at the number of heads. Yes, I know you expect it to be 50 without calculation, but can you tell me how far off you're going to be? You can, if you just apply what we've done today. So if I'm tossing a coin 100 times, then the number of heads is like the sum of 100 draws from the box 0, 1. 0, 1. These are the number of heads that you can get on one toss. Either no heads or one head. And these proportions are fine because the chance is half and half. So let's examine that one toss. The average of that box is clearly a half. The SD of the box is, well, 0 minus a half squared plus 1 minus a half squared, and then you average that, and then you take the square root, and the SD of the box is 0.5. This can be seen in very many different ways. For now, I'm just going to do the straight calculation. We're going to be looking very hard at this box in the future. So on a single draw, you expect to get, in the long run, 0.5, give or take about 0.5, and by formula, the expected sum of the draws, which is the expected number of heads, is number of draws times the average of the box, which is 50, which you knew already. And now the standard error of the number of heads is square root of the number of draws times the SD of the box, which is 5. And so in 100 tosses, you expect 50 heads, give or take only about 5. So you would not be surprised to see heads in the range 50 plus or minus 5, 50 plus or minus 10, 50 plus or minus 15, and after that things start to get rather unlikely. In fact, I'm going to say the overwhelming probability is in the range 35 to 65. And what's that again? That's 50 plus or minus 3 standard errors. I'm saying the overwhelming probability is in that range. And I can hear some of you saying, wait a minute, hang on. Overwhelming? That's strong language, isn't it? Chebyshev is telling me that outside the range 35 to 65, I have at most 1/9 of the probability. 1 divided by 3 squared. So inside this range, I have at least 8/9 of the probability, and at least 8/9 is a very large probability, but am I sort of exaggerating a little by the word overwhelming? Well, let's take a look at what the probabilities actually look like, and there they are. These are the probabilities. It's a probability histogram for the number of heads in 100 tosses of a coin. And just to be certain that you understand no magic has happened here, you should be confident that you can calculate each one of these probabilities. So there's the central bar at 50. Its area is the chance of getting 50 heads in 100 tosses, and that you can find by using the binomial formula: n is 100, p is 1/2, and k is 50. Right, so this bar here is the bar at 60. Its area is the chance of getting 60 heads in 100 tosses. So n is 100, p is 1/2, and k is 60. You can use the probability calculator in your text or any other calculator you have, and you can calculate each one of these bars. That's exactly how it's been done. And now look at the horizontal axis. This represents the number of heads, and so it stretches from 0 to 100. That's the possible number of heads in 100 tosses. But can you see any probability here? You can't, because on this scale it is so small that it is invisible in the picture. It's there, it's not 0, but it's so small that you can't see it. So where can you see the probability? Well, there's 40, there's 60. Sure looks to me like you're looking at 35 through 65. And so I think I'm quite justified in saying the overwhelming probability is in the range 35 to 65. Chebyshev says at least 8/9, but it's quite a bit bigger than that. And why is that? Well, because now we can see the shape of the distribution, and the shape of the distribution looks like what? Yeah, it looks like a very familiar curve. It looks like the normal curve. And in the normal curve, center plus or minus 3 measures of spread picks up pretty much all of the area. And that is what is going on here. And so in the next segment, we're going to see, all right, we've identified the center of the distribution, we've identified a measure of spread. If we knew the shape was normal, we could find any probability we wanted to. So is the shape normal? Under what conditions?